Good morning and Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering. And today my lecture topic is Control Memory from subject Computer Organization and Architecture. So the overview of presentation include instruction and the types of instruction in control memory, control memory reduction, micro instructions, and construction of control memory word. So what is control memory? Control memory is an address register specifies the address of the microinstruction and the control data register that holds the microinstruction, and it will be acting as a read-only memory. The control memory is assumed to be a ROM memory which store all the control information. So CPU is composed of two things. One is arithmetic and logical unit and one is your control unit. So control memory is being the part of our control unit, and the control unit will consist of these four blocks. First one is our next address generator. In next address generator, the external input is inserted that will be coming from your system, and the address generator will generate an address. That address is stored in a car register, which is a dedicated register used for control memory. Now this control address register will be containing the addresses of micro instructions. These micro instructions are stored in our control memory unit, which will be predicted as a ROM memory. Now from here the address will be generated, and that address, at that particular address we will find a micro instruction in control memory, and after that after execution of that instruction, the data is being given to your control address register, which is known as the CDR register. After that the instruction is being fetched into a control word. In control word the micro instruction is being processed, and after that it will be executed on the basis of the segregation in a control word, and that micro instruction will perform some micro operation accordingly. So in the end of this lecture we will come to know how this control word is constructed and how this micro instruction is being fetched and decoded. After this construction of this, the address of the next instruction is being generated by the external input, and then next address will be generated for next micro instruction. So it is a cyclic process, and it will be go on till your micro instruction will be completed, which are stored in a control memory of a control unit. Now what is a micro instruction? The micro instruction contains a control word that specify one or more micro instruction for the data processor. The address sequencing capabilities required in control memory are: the first one is the unconditional branching and the conditional branching, that will be the part of your this control word. A mapping process that will map a bits of instruction to address for a control memory, to generate an address for a control memory, and a facility for subroutine call and return. Whenever some branch will occur or conditional branching will occur, that address need to be set somewhere, and then the current branching instruction will be executed, and after completion of execution the control will come back to your main instruction, which has been halted because of the branching process. So in short, micro instruction is a part of instruction itself. Instruction is being converted into a micro instruction, and these micro instructions are being stored in your control memory, and then it is executed. Now what is a control memory and how this functioning is being done in a hardware, in our computer system? Now from the external source, instruction code will be fetched, and that instruction will be obtained through converted into a micro instruction using a mapping logic. Here the multiplexer will give the choice among the four types of address opportunities, which will be having location 0, 1, 2 and 3. So there are four ways of getting the address of a micro instruction. Micro instruction, there are four ways of getting the address of micro instruction, which is being stored in our control memory. So reaching here, which of the micro instruction is being used, being processed, there are four ways of obtaining the address of that particular instruction. One of the way is to get an address from the external source. The instruction is being fetched from the memory, and that instruction is being converted into by using a mapping logic into our micro instruction address, and then we will get the address, and that address will be stored in your this CAR register, that is control address register. That is the address of the current micro instruction which is being stored in your control memory. One way is like this, doing this mapping logic, which will be I'm discussing later. And the another way is getting this. Suppose this address we will be getting, and at that address some branch will occur. There will be an instruction in a control memory that will be containing a branching instruction itself. Then at that moment the instruction will be the address of instruction will be incremented for the further, and that previous instruction will be stored in the subroutine call register in order to come back to the instruction which is previously being held, as we got some branching or conditional or jump statement in your current instruction. So from the control will be jumped from that instruction to the instruction which will be performing a branching operation. So the in between sequenced instructions are skipped. For returning back to those instructions in the sequence, we need to store that address somewhere. So we will be storing that address in subroutine call and incrementing the address and getting back to this position for branching statement. And for subroutine call, we will follow this location number 1 in a multiplexer. So this is the case of branching. So one is the branch unconditionally and one is the branch with the condition. Okay, like if I is greater than 0, then you have to proceed for a branching. These are the conditional branching, an example of conditional branching statement. So in conditional branching, what we will be doing, the address will be generated by the instruction itself, and that address will be processed in the location number 3. And along with that, the status bit which will be stored in a branch logic block will also be checked whether the condition is there or not. If there the condition exists, this branch logic status bit will be actively 1, and if it is the branch conditional statement is not present, it will be 0. So for that logic, this branch status bit will be reached here in branch logic, and the branch will be taking place. Okay, at location number 3, we will be getting the address of such instructions which are having the branch with your conditional statement. And if we are having some that branch logic without a condition, then we will be incrementing it and storing the address of the previous instruction which we want to return back in your subroutine register, that is the SBR register. So we in 4-way incrementation by 1, like we will be doing the PC equals to PC plus 1, or by recovering that previous address which is stored during the time of a branching statement from this subroutine call. So we are having 4 choices. With the help of this multiplexer, we will make the choice among any one of them. If this branch logic is selected to here, we will select the marks. It will be 0 0. It will be selecting line 0 0. Then this 0 location will be selected. If it is selected to be 0 1, then 1 will be selected. If it is 1 0, then 2 location will be selected for the location, and we will be get output the address line of location number 2. Similarly for 3, we will be having 1 1. Okay, so this is the way how we will obtain the address of micro instruction which are being stored in the control memory by using the 4 different procedures that I discussed. So what is the mapping logic? How this mapping can be done when if the instruction is being received from the external source. So what is that mapping logic? In mapping, what we will do, this is the instruction, we can say 16-bit of instruction which is being fetched from the memory, which is somewhere in the memory, that is in a RAM itself, and it is fetched and we can say decode, or which is fetched in an IR register, that is instruction register. What will happen in that? So what will be happen? 0 to 11 will be reserved for the address portion, that 16-bit first low order 11 bits will be of address, and the 3 will be of opcode and 1 will be the mode bit. Okay, what we will do if we achieve the address, this 16-bit of address from some external source that is fetched from the memory or given by the CPU, then how to convert that into a micro instruction address, that is this diagram is talking about. So if we get this address portion, we do not need those bits to be here because that will be of no use in this concern in mapping logic. So we will be having focus on this opcode bits. So we are having 3 bits of opcode and 1 is the mode bit. So how to convert them? We will directly copy them as it is, like 1 here, this 0 will be copied as it is over here, this 1 as it is over here, and then again 1 and this one. So we have to construct a 7-bit of address over here. So what is the logic behind this 7-bit of address? As according to this, we are following the Morris-Minnow book, the control memory will be of 128. So 128 is 128 into 12, I think they will be taking this configuration. So 128 is equals to raised power 7, and this power will be your number of address line into 12. 12 is your data lines. So that's why we are considering that 7-bit of address for these micro instructions which are being stored in your control memory. That's the logic behind this 7-bit. We can take it 8-bit, 12-bit also, 14, 16, anything. That will be according to the configuration of the memory which we are taking. And taking the power of 2, we will be considering the power to be the number of address bit for that. So here we will be copying this opcode as it is, and we are inserting 0 at most significant location, and on the 2 lowest significant bits, LSB1 and LSB2, we will be inserting the 0, and 4-bit we will get as it is, which are copied from the opcode, and in the most significant location we will be inserting 0, and in the low significant 2 locations we will be inserting the 0 again, and we got 7-bit of address of the micro instruction, which is given by the CPU, or which will be given from the external sources. So this address, which is the part of 16-bit of instruction, will be converted into a 7-bit of, we can say, address of micro instruction. So this is the mapping logic. After getting the address of that particular instruction which are being stored in this control memory, what will be the next step? The next step is to decode that instruction to obtain which kind of task is being performed by that instruction in a control unit. So the next is, after mapping logic and all, construction of that micro instruction to segregate that we can say instruction into this. That address will be of 7-bit, but that instruction is not of 7-bit, that will be of 3-bit, and F3 of 3-bit. What are these 3? These are micro operation fields which will be telling us which kind of operation is being performed by that micro instruction, which we obtain on that particular address in your control memory. Then we have CD, that is for checking whether the conditional branching exists in that micro instruction or not. Then we are having a branch field, again showing whether the branch is present in the instruction or not. And then we have the address field. Now what is the role of this 7-bit of address field? That is the address of next micro instruction. Now if this branch will exist, what will happen? The address of that this current address will be stored somewhere in a subroutine call register, and we will jump to the branching we can say micro instruction. But in this case, if there is no conditional statement, no branching statement, the next micro instruction will be sequentially addressed, that is the address present here plus 1, that is the micro instruction in that present in the sequence in a particular pattern. Okay, so combining these 3 bits, this is the complete control word of a micro instruction. That will be okay 20 bits. Okay, so this is the segregation of that 20-bit of micro instruction in our computer system. Okay, for 128 into 12 line we can say control memory. Okay, now the next is how we can convert those binary bits into a micro instruction or some given format into a micro instruction. So for that purpose, we are having some tables of these micro operation field. Like for F1, we are having these 7 micro operation. Okay, at a different location. Like at 000, no operation will be performed. Okay, at 001, we have a addition operation between the accumulator and the data register, AC and DR, add operation. And then at 0010, so these 3 bits will decide which of the micro operation is being performed in field number F1. Out of these 7, only 1 micro operation will be performed at a time. Like we are having clear the accumulator, then increment the accumulator by 1, copy the content of, transfer the content of data register into accumulator. As accumulator itself is a data register, it is a temporary or intermediate data storage register. Like next is transferring the data of address register or program counter into address, because both are the container of addresses at location 110. means if the F1 is containing the binary bits 110, then we have to perform this particular operation. Then we have a write operation also. In write operation, we have to transfer the content of this data register into some memory, M of AR. M of AR means in main memory address, some address of the main memory where this content needed to be stored. So these are the 7 operation of F1, micro operation of F1 block. Similarly for F2 block, what we are having, again at 000, we have a no operation. 001, we have a subtract operation, subtraction between what? The data register and the content of accumulator will be subtracted. Binary contents will be subtracted and then stored again in a accumulator. Now in OR operation at 010, what we, these are like this: binary 0, binary 1, code 2, 3, 4, 5, 6 and 7. Similarly for this one we are having 7, and similarly for this one again we are having 7, like 0, 1, 2, 3, 4, 5, 6 and 7. Okay, so in this OR operation we are performing the logical OR operation between the accumulator and data register for binary bit 2, and for this AND operation, logical AND operation will be performed between accumulator and the data register. In read operation, some content of memory will be at this particular address which is present, which is given in the instruction itself. That content will be read and copied into your data register. Okay, and then this transfer of content of accumulator to data register, then incrementing the data register by 1 value and updating it, and then transferring the content of program counter to data register. But some particular bits, that is from 0 to 10 bits, will be transferred from the program counter to data register, because program counter may be of 12 bit. So starting from 0 to this 10, these 11 bits, the rest of the 11th and 12th bit will be discarded in case of program counter. Okay, as we are considering a 12 bit of address in this particular material. Okay, 12 bit of address. So first low order 10 bits will be transferred, means the content of program counter will be transferred to first low order 10 bits. Obviously the 10 low order bits of program counter address will be transferred into the. Similarly in F3, what we are having, again we are having 7 micro instruction. First one is again the no operation. At 00, no operation will be performed if these 3 binary bits are present in F3. Again in XOR, that is logical XOR operation between the data register and the accumulator will be performed. And then the complementing means inverting the value which is present in the accumulator. SH shift left operation in accumulator, then SHR is a shift right operation with the accumulator, shifting 1 bit towards the left, shifting 1 bit towards the right, those kind of operation, shifting operation. And INC PC means increment the content of program counter by value 1. Then ART PC means transferring the content of again address register to your program counter. And then 111 is some reserved bits. Here some no operation will be performed, but some reserved operation will be performed. So these are the 3 tables at if such kind of bits, 3 bits of combination are present. So which kind of micro instruction will be present in your that control word. So these table need to be followed for. Now what about next 2 fields, that is CD and BR here. So we have already discussed these 3 fields. What about CD and BR field? How that will be of 2 and 2 bits. So how we will come to know what conditional branching is present, whether the branch is present. Okay, so there are 4 combinations for this, means 4 values are present for this, that is at location 00, 01, 10 and 11. So at 00 we are having unconditional branching. U symbol will be inserted at that place. That means the branch will exist without any condition, but where there will be the existence of a branch. Okay, next is indirect address bit, kind of means number 15 bit will be checked for the location and the symbol will be inserted as I, that is the indirect addressing bit for conditional branching. Next is sign bit of AC will be checked, whether the 15th bit jo hai, that will be 1 or 0, that will be the sign bit. Either it will be 1 or that will be the represented with the symbol S, and then the 0 value in AC will be checked whether your accumulator is having 0 inserted in it or not. All the data is cleared. That kind of conditions are being checked over here with these locations 0, 0, 0, 1, 1, 0 and 1, 1. If nothing is present in the CD, that it is automatically at 0, 0. Okay, we will not keep that field in your control word empty. We will insert 0, 0 value if something is not present, no binary bit is present. Now next is about BR, that is the branch logic. In branch logic, we are again having divided into 4 type of instructions for combination of 0, 0, 0, 1, 1, 0 and 1, 1. The first one is the jump statement in the branching. As we know that what is jumping, jumping means the control will be, if we will get some jump statement over here, the control will jump from here on that particular, suppose we are having this address and this address we are having over here, will jump, the instruction will give the control to that instruction which is being present in that jump instruction. So jumping is skipping some in between instructions and going to some instruction which is far beyond from that instruction and having address in itself. So in that case, we need to reserve the address of this next instruction in the sequence in order to come back to that instruction when this jumped instruction is being completed. That is the concept of subroutine call and return. Okay, so that is jump statement. Here what we are having, the functionality, the address is being uploaded in the car, that is the control address register, that is the personal register of your control memory, and the condition will be checked. If it is, the condition is 1, then in that content will be uploaded in that from the address register and it will be again incremented by 1. Okay, and the condition will become 0 after completion of that operation. Now next is, if the binary bit 0, 1 is present, then the call kind of we can say branch logic will be performed. In this kind of branch logic, the address is being copied into car register and the incremented value will be stored in your subroutine call, which I have already shown in your that block diagram, and the condition will become 1 for this, and again after performing this operation the condition will become 0 after incrementation of control address register y1, that is the address in and the address of the next instruction in the sequence. The next in RET return, in this this is the logic I am talking about. When this jump will be occur and that jumped instruction is being performed and executed and completed, we have to come back to the next instruction in the sequence. For that, what will we do? We will use this return instruction, and the address where we have to return is being stored in the subroutine call register. Suppose we are having here 0000 address, this is 0001. Okay, and this statement is saying that jump to 003 address. So we will go here. What about these instruction which is in the sequence 001 and 002? So what will happen at the time when we are jumping from here to here, we will be copying this next, because this program counter is containing the address of next instruction in the sequence. So what will we do? We will copy the content of PC to SBR. We can say that is 0001. So whenever this branch will be get completed, the address in the car will be updated as 0001 and we will come back to this particular instruction in the sequence. That is the logic of subroutine call and return. That will be performed with the help of the subroutine call register in control memory. But if we are talking about this simple RAM, there we will be using program counter for this. Okay. So next is the mapping logic that I have already discussed with the help of diagram, that we have to copy the opcode bits, that is 14 to 11 bit directly into car register, and then inserting at 0, 1, 6 and location 0 to perform to make a 7-bit of address. So that's all about this control word. Thank you and Jai Hind.